Thank you for joining me today. My name is Kendall Rogers. I work at Thrust Belt Imaging in Calgary, Canada. Today I will be presenting a case study of complex structure seismic processing with model move-out. This presentation was originally given at the AAPG Regional Convention in Cyprus in May of 2023. The data consists of 10 2D lines acquired in 2019 and is situated in northwest Greece close to the Albania border. Today we will focus on the eastern portion of this 2D line as it contains the Aphrodite prospect, which is a main area of interest. The data had been previously processed and we can look at the legacy depth stack here. I will draw your attention to the vertical exaggeration, which is about a 3-to-1 ratio. At the start of our work, we had three primary objectives. The first was to image the top of the reservoir. The second was to better image the area above the Aphrodite prospect, which is this area here. And the third was to better resolve the near-surface seismic data with the surface geology. This is a comparison between the legacy depth stack and the results of our work with Energean in 2022. We can overlay interpretation provided by Energean. The blue is the top of the reservoir. Next is the area above the Aphrodite prospect, followed by the fault interpretation and the top of the fleece on the west side, and some reflectivity within the carbonates on the east. And once again without the interpretation. The workflow has been divided into three main processing steps: modeling the near-surface velocities, anisotropic depth imaging. It is pretty standard across the industry to apply the time statics derived from the near-surface velocity model, as well as residual statics to the data prior to depth imaging. The third step is incorporating the near-surface velocity model into the depth velocity model, in place of using the time statics as in step 2. This step can only be done once the depth velocity model has been finalized in step 2. Also, the residual statics have to be recalculated because they had previously been coupled to the refraction statics. So for step 1, modeling the near-surface velocities, this involves the standard approach of modeling the near-surface velocities and calculating associated time delays. The near-surface velocity model does not capture all of the time delays in the near surface, and so residual statics are also used to define as much of the delays as possible. These are examples of shot records. Each one is showing 2,000 meters of offset. We can see that the direct arrival energy is coming in about 200 milliseconds earlier on the shot on the left-hand side than it is on the other two. This points to a faster velocity in the area of this shot record. The time offset pairs for each shot and receiver combination are recorded and can then be used to model the near-surface velocities. This is the near-surface velocity model derived in this way. The color bar on the left shows a large variation ranging from about 1,800 meters per second to nearly 5,000 meters per second just above the base of weathering. The seismic energy has to travel through the near surface as it leaves the shot and on its way back up to the geophone. So extreme variations here can really distort the imaging at depth. This is a cartoon of the previous slide. You can imagine the near-surface velocity model that we just looked at fitting here between the surface and the base of weathering. Refraction statics are calculated vertically within the velocity model, which only approximates the actual ray path as seen here. Reflection statics. Since refraction statics only account for some of the time delays caused by velocity variations, there is a residual component that still needs to be calculated and applied to the data prior to depth imaging. The calculation of these statics is done by flattening reflection energy on the gathers using the NMO equation, and then running cross correlations on traces that have similar coordinates and offsets. From this, we can derive static values for each individual shot and receiver. If we take a look at an unmigrated stack before and after total weathering statics application, there is an obvious improvement in reflector coherency and imaging. That takes us to the end of step 1. The time delays have been calculated and applied to the data, which is then ready for anisotropic depth imaging. Building a depth velocity model in an exploration area like this is difficult. Thankfully, we did have extensive and detailed surface geology information and were able to extract rock type and dip information along the 2D lines. And once again, just showing the area of this 2D line that we were looking at today. We can see that information displayed at the top of the pre-stack time migration stack here. To begin the model building process, Energean interpreted the pre-stack time migration stacks for each line and provided the horizon interpretations. Filling in the velocity values for the first model is done by using information from the RMS velocities that were used in pre-stack time migration, along with general knowledge of rock velocities for the given rock types seen in this area. To begin with, model updates were done by analyzing post-migration gathers and stacks with post-migration move-out applied. Energean and TBI agreed that progressing as far as possible with this methodology prior to incorporating any interpretation would limit any bias from previous interpretations on the legacy results. After about 7 iterations on each line, pre-stack depth migration stacks were created and given to Energean for analysis. This is when we started trying out different interpretations. This next slide toggles through some of the intermediate velocity models so you get a feel for the types of interpretations that were being tested on this particular line. The data is migrated with each intermediate model and the results are analyzed to determine if the model has resulted in improved imaging. It is important to change one thing at a time during this process so it is clear what changes are improving the resulting stacked image. We ultimately end up with a final velocity model and corresponding stack for each 2D line. The legacy stack and the current results both use Kirchhoff anisotropic depth imaging with the same technique of applying refraction and residual statics to the gathers prior to migration. You can see there is improvement throughout the line, but what I want to point out is the improvement in the shallow areas. Good reflectivity here means the shallow part of the velocity model is more accurate. Errors in the shallow portion of the velocity model mean the ray paths are incorrect well before they reach the target level. Moving on to the third and final processing step, which again is anisotropic depth imaging, but now with model move-out. The results from step 2 are the end of a typical workflow, but there is an opportunity to improve the final image by addressing 2 elements of the workflow. The first is the weathering statics that were calculated using the near-surface velocity model. The second is implementing a more accurate way to flatten the gathers prior to the calculation of residual statics. Previously, we used the normal move-out equation, which flattens gathers using an RMS velocity field, which is less accurate the more the velocities change. So the first change is to remove the refraction statics. We still want to account for the time delays caused by the weathering layer, but instead of using the statics approximation, which uses the vertical ray path, as seen here, we are going to replace the top 300 meters of the depth velocity model with the near surface velocity model and ray trace through those velocities instead of applying a time static to the gathers prior to migration. This comparison shows the difference between using the refraction statics and ray tracing through the near-surface velocity model. For a fair comparison, I removed the residual statics from both solutions. So on the top, we have the pre-stack depth migration with refraction statics. And on the bottom, we have the pre-stack depth migration with no statics at all, just ray tracing through the new depth velocity model with the near-surface velocity model superimposed. There's an area here on the east side that shows improvement. So there was some complexity in the near-surface velocity model that couldn't be handled well by the vertical statics approximation, something that ray tracing was able to improve upon. Model move out. We are using the travel times from this new velocity model to flatten the gathers prior to calculating the residual statics. This is in contrast to the previous method of using the NMO equation with a less accurate velocity model. The next step is to apply the new residual statics to the data and remigrate. And now the difference between step 2 and step 3. So again, for step 2, we are applying the full weathering statics, both refraction statics calculated from the near-surface velocity model and the corresponding residual statics calculated using the NMO equation to the data prior to migration. For step 3, in place of the refraction statics, we instead ray trace through the near-surface velocity model and we recalculate residual statics using model move-out, which is flattening the gathers using the final depth velocity model. Now, it makes sense to expect the most improvement in areas where there is a lot of variation in the upper part of the velocity model because, for one, that is where the vertical ray path approximation for the refraction statics calculation would break down the most. And secondly, that is where the NMO equation would be its least accurate. That is exactly what we see here. The west side is all slow, fairly uniform rocks, and there's very little difference between the results. Also on the east side, where it is all carbonates, there isn't much difference. It's in the middle area where we go from molasse to fleesh to carbonates, back to fleesh and then carbonates again, that we see the majority of improvements. And final comparison between the legacy processing and the final migration with model move-out. The interpretation from Energean shows an update on the top of the reservoir and a pretty stark contrast between the shape of the Aphrodite prospect. The area above the prospect shows a tight fold and more clear imaging of some steep reflectors. There is a new fault interpretation. The molasse and fleesh on the west side has much better bandwidth and continuity, and the bedding within the carbonates is far better on the east side. In conclusion, there is a new way to correct for near-surface weathering. In place of the refraction statics, which are calculated from the near-surface velocity model, we introduce a ray tracing approach that merges the near-surface velocity model with the depth velocity model, thereby removing the assumption of a near-surface vertical ray path. This, coupled with the model move-out approach of flattening gathers for residual statics calculation, results in a more sound methodology and superior imaging.